Good day, everyone. Today we'll be presenting Ensuring Safety in AI-based Self-Driving Systems. AI-based self-driving systems are becoming one of the most significant uses of artificial intelligence in transportation. These vehicles use cameras, LiDAR, and radar to sense the environment, while deep neural networks process that sensor data to identify objects and support driving decisions of the vehicles. Unlike traditional software, their behavior is shaped by training data rather than by explicit pre-written rules alone. They are being adopted for several reasons. They could reduce human error-related crashes, improve traffic flow, and increase mobility for elderly and disabled population, and also lower the costs associated with road accidents. Our slide also highlights that human error is linked to around 80% of fatal collisions in Canada, which explains why interest in automated vehicles is growing so quickly. However, safety is a critical issue. Deployment is accelerating faster than regulation, and without strong safety assurance, both public trust and human lives are at risk. That is why this topic is not just about innovation, but about proving these systems are safe enough for real public roads. And with that, it brings us to the central engineering problem behind this technology, so now I'll hand it over to Ahmad.
The core problem we are addressing is this: how can engineers prove that AI-based self-driving systems are safe enough for public roads? There are three main issues. First, there is a mismatch with current safety standards. These frameworks were designed for deterministic systems where behavior is predictable and traceable. Second, AI systems can behave unpredictably since they learn from data. Their performance depends on the training data and how they respond to new or rare scenarios. Third, there is a lack of certification methods, meaning there is no established frameworks to fully verify AI safety. Because of this, engineers cannot yet provide strong evidence-based safety guarantees. To understand why this is difficult, we need to look at how these systems actually work. Self-driving AI systems operate in three stages: sense, decide, and act. Sensors such as cameras, lidar, and radar collect real-time data and detect objects and hazards. Neural networks then process this data to identify objects, predict movements, and select actions. Finally, the systems execute those actions through steering, braking, and acceleration. The key issue lies in the decision stage. Because the neural networks learn from their data rather than fixed rules, their decisions are often a black box, meaning engineers cannot clearly explain why a decision was made. This is why current safety methods struggles to evaluate these systems.
So why do current safety methods fall short? One reason is that they are not designed for systems built around machine learning. Modern standards, notably ISO 26262, assume software behavior is fixed and fully traceable. With AI, however, that assumption breaks down. Machine learning models are sensitive to subtle changes in their environment. This makes their behavior practically non-deterministic, meaning seemingly matching inputs may yield drastically different outputs. For instance, a car approaching a stop sign may brake 10 seconds early one day and then 5 seconds early the next day, all because a different shadow was cast on the stop sign. This unpredictability fails to pass safety certifications. Additionally, AI models are trained on massive data sets rather than programmed line by line. This results in black boxes, where we can see their inputs and outputs, but their internal reasoning remains completely hidden. The lack of explainable decisions in these systems makes errors untraceable during debugging, preventing engineers from pinpointing exact failures. This will once again fail to comply with contemporary safety standards. Currently, AI safety research relies on narrow benchmarks that rarely relate to actual certification standards, creating an evaluation gap between technical performance and safe public deployment. To understand why this gap is challenging to close, we need to examine the specific safety challenges involved.
To see why this is so difficult to close, I will now explain the main safety challenges in more detail. The safety challenges for AI-based self-driving systems can be grouped into three levels: data, model, and system. At the data level, training sets can be biased, important edge cases may be missing, and behavior can still shift after deployment. Additionally, there is still no clear standard for what counts as enough data for safe operation. At the model level, engineers face black box decisions, vulnerability, difficulty verifying robustness, and the lack of an agreed certification method. At the system level, the vehicle must operate in unpredictable environments, handle cybersecurity risks, as well as manage the added complexity of multiple interconnected components. This includes systems that may continue learning after deployment. While most research targets technical areas like fairness and robustness, very little address policy and regulation. This gap suggests that the challenge isn't purely technical. Ultimately, it's about how we translate engineering evidence into industry standards and regulatory approval. So once those challenges are clear, the next step is to look at the engineering approaches that can help address them, which Owen will cover that now.
Although no single solution fully solves the problems, the research points to three important engineering approaches. The first is certification-oriented analysis, which means examining machine learning models in specific use cases, using tools such as robustness testing, uncertainty estimation, and explainability methods like saliency maps or surrogate models. These methods can help the engineers produce evidence about how a model behaves and where it might fail. The second approach is integrating AI safety methods with existing automotive standards like ISO 26262 and UL 4600. Instead of replacing traditional safety frameworks, engineers can combine them with machine learning verification and testing so that AI-specific evidence supports the established safety processes. The third approach is lifecycle-wide safety assurance. Safety must continue after certification through monitoring, field data collection, and updating plans for systems that adapt after deployment. This slide also includes real-world evidence from Waymo, reporting fewer serious injury, and cyclist injury crashes than human drivers, which suggests that measurable safety gains are possible when strong assurance methods are used. In conclusion, our presentation shows that current methods are still not sufficient to fully certify AI-based self-driving systems. Existing frameworks break down because they were designed for traceable, rule-based software, while AI systems are data-driven, harder to interpret, and more difficult to verify with traditional methods. That is why a combined approach is necessary. Engineers need to bring together robustness analysis, uncertainty estimation, explainability, structured safety cases, and integration with existing automotive standards. Just as importantly, safety has to be lifecycle-wide, with post-deployment monitoring and adaptive safety management rather than a one-time certification event. Our recommendation is that researchers, industry, and regulators must work together to close the gap between AI safety research and real certification practice. By combining technical evidence with established safety frameworks, engineers can move towards self-driving systems that are not just advanced, but genuinely trustworthy for public road deployment. Thank you for listening.